On December 27, 2004, for exactly 4 days, humanity faced its highest asteroid threat level ever recorded. An object called Apophis had just earned a rating of 4 on the Torino Impact Hazard Scale, a scale that goes to 10, where 10 means certain global catastrophe. No asteroid before or since has climbed so high. The news spread quickly. A space rock the size of 3 football fields had a 1 in 37 chance of hitting Earth on April 13, 2029. A Friday the 13th. The probability may sound small, but consider this. Those are better odds than drawing a royal flush in poker. And the stakes? If Apophis struck, it would release the energy of 1,200 megatons of TNT, 24 times more powerful than the largest nuclear weapon ever detonated. Cities could vanish. Coastlines could be erased by tsunamis hundreds of meters high. Millions could die. Then, as suddenly as the threat appeared, it vanished. A single photograph, taken months earlier and nearly overlooked, changed everything. Within days, scientists declared Earth safe. Apophis would miss us. But here's what makes this story remarkable. That near miss in 2029 isn't the end. It's the beginning. Because on April 13th, 2029, yes, that same Friday the 13th, Apophis will pass so close to Earth that 2 billion people will be able to see it with their naked eyes, moving across the sky like a slow meteor that never burns up. Closer than our satellites. Close enough to fall through the gap between Earth and our artificial moons. And when it passes, something even stranger will happen. Earth's gravity will squeeze Apophis like a hand crushing an aluminum can, potentially causing the asteroid to crack, shift, and even ring like a bell. We will witness, in real time, a planet warping a space rock. The Serpent of Chaos, once feared as a world killer, will become the most intensively studied asteroid in human history, and teach us how to save ourselves from the next one that doesn't miss. Tonight, we'll follow the story of Apophis from panic to promise, from chaos to opportunity. We'll travel back to that June evening in 2004 when 3 astronomers spotted a faint dot of light that would soon set off alarm bells across the world. We'll explore how scientists refined their predictions, eliminating the threat year by year through patient observation. And we'll look forward to that April night when Apophis will perform the closest flyby of an asteroid this large that humanity has ever witnessed in advance. Hello there, and welcome to the Sleepy Science Channel. I'm so glad you found your way here. Maybe you've had a long day, or perhaps you're the kind of person who drifts off best when contemplating the grand mysteries of the cosmos, rather than counting down from 100. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your thoughts soften, your breathing deepen, and your mind wander gently through space and time. Because tonight, we're not just learning about an asteroid. We're exploring one of the most remarkable stories in modern astronomy. A tale of discovery and dread, of precision and patience, of human ingenuity turning a potential catastrophe into the scientific opportunity of a lifetime. Along the way, you'll hear about the invisible forces that nudge asteroids across millions of miles, the scales we've invented to measure cosmic threats, and the spacecraft missions racing to meet Apophis before it arrives. Some of what you hear may surprise you. Other details might simply float by like dust motes in sunlight, gentle and forgettable. That's perfectly fine. This isn't a test. It's a drift through the quieter corners of space science, where numbers become poetry and orbital mechanics feel like a lullaby. And just before we begin, if these calm explorations help you unwind or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin our journey. Let's travel back to a warm June evening in 2004 to a mountaintop observatory in Arizona, where 3 astronomers were about to discover something that would change how we think about the sky above us. The discovery: a dot of light that changed everything. The night of June 19, 2004, began like countless others at Kitt Peak National Observatory in southern Arizona. Perched atop a mountain in the Sonoran Desert, Kitt Peak has long been a sentinel in the search for near-Earth objects, those cosmic wanderers whose orbits bring them uncomfortably close to our home planet. The air was clear, the stars sharp, and 3 astronomers, Roy Tucker, David Tholen, and Fabrizio Bernardi, were methodically scanning the sky. Their equipment wasn't hunting for anything specific. Instead, they were part of a broader effort to catalog near-Earth asteroids, building a census of rocky objects that might, one day, pose a threat. This work had been ongoing for decades, gradually accelerating as technology improved and funding increased. In the 1990s, NASA had established the Space Guard Survey, a program designed to find at least 90% of near-Earth asteroids larger than 1 kilometer within a decade. The effort was motivated by growing recognition that asteroid impacts, while rare, represented a genuine threat to civilization. The work required patience and dedication. Night after night, telescopes captured images of the same patches of sky. When astronomers compared images taken hours apart, most of the stars remained fixed, pinpoints of light that had been in the same positions for millennia. But occasionally, something would move. A faint dot shifting position against the stellar background. An asteroid. These moving objects were the quarry, and finding them was like searching for needles in a cosmic haystack. Most were harmless, distant objects that posed no threat, but every so often, one would be close enough, large enough, or on a trajectory worrying enough to warrant further investigation. The discovery process itself is a marvel of modern astronomy. Powerful CCD cameras capture wide-field images of the sky, recording the positions of millions of stars and other objects. Sophisticated software compares images taken at different times, flagging anything that is moved. The flagged objects are then examined by human astronomers who determine whether they're genuine asteroids or merely artifacts. Cosmic rays hitting the detector or distant satellites. If confirmed, the object's position and motion are reported to the Minor Planet Center, a clearinghouse for asteroid observations maintained by the International Astronomical Union. From there, orbit calculators at NASA's Jet Propulsion Laboratory and other institutions begin the work of predicting the object's path through space. On that June night, they found one, a small point of light, unremarkable at first glance. They tracked it for 2 nights, noting its position, calculating its preliminary orbit. Then, as so often happens in astronomy, technical difficulties and cloudy weather interrupted their observations. The asteroid, temporarily designated 2004 MN4, vanished back into the vastness of space. Here's the unsettling part. If the weather had stayed bad for just a few more weeks, Apophis might have slipped away entirely, lost in the glare of the sun's position relative to Earth. The asteroid would have remained undiscovered, and when it appeared again months later, there would have been far less time to refine its orbit and understand the threat. The difference between finding an asteroid early and finding it late can mean the difference between having decades to prepare and having only years, or worse, months. In Apophis's case, that brief 2-night observation in June, nearly cut short by weather, ended up being crucial. But the data had been logged, and in the months to come, that data would tell a story that sent ripples through the astronomical community. Other observatories picked up the trail. In December 2004, a team at Siding Spring Observatory in Australia relocated the asteroid. With more observations, its orbit became clearer, and as the calculations refined, something unsettling emerged. This wasn't just another routine near-Earth object on a distant pass. This asteroid, 2004 MN4, was going to come very, very close to Earth. And there was a date, April 13th, 2029. Initial calculations suggested something even more alarming. There was a chance, small but real, that the asteroid might not just pass close. It might hit. The probability hovered around 2.7%. In statistical terms, that's roughly 1 in 37 odds. Not likely, but far from impossible. For an asteroid estimated to be more than 300 meters across, large enough to devastate a region the size of a small country, those odds were unacceptable. The asteroid was assigned a rating on the Torino Impact Hazard Scale, a tool astronomers use to communicate the level of concern warranted by near-Earth objects. The scale runs from 0, indicating no hazard, to 10, representing a certain collision capable of causing a global catastrophe. For a few tense days in late December 2004, MN4 reached level 4 on the Torino scale. It was the highest rating ever assigned to any asteroid. No object before or since has climbed so high on that scale. Level 4 meant that close attention by astronomers was warranted, and that public attention was likely. And indeed, the news spread quickly. Headlines around the world announced the discovery of an asteroid that could strike Earth in 2029. The odds were reassuring to scientists, familiar with probabilities and confident that further observations would refine the orbit. But to the public, the news was jarring. An asteroid named after an ancient god of chaos, hurtling toward Earth with a non-zero chance of impact. The name Apophis had been chosen deliberately. In Egyptian mythology, Apophis, also known as Apep, was the great serpent, the nemesis of Ra, the sun god. Each night, as Ra traveled through the underworld, Apophis would attempt to swallow him, plunging the world into eternal darkness. Though Ra always triumphed, the battle was never over. Apophis represented chaos, destruction, and the ever-present threat of annihilation. For an asteroid that seemed poised to threaten Earth, the name captured both the danger and the ancient primal fear of objects falling from the sky. But even as the media ran with the story, astronomers were working tirelessly to gather more data. Every new observation narrowed the uncertainty. Every additional measurement refined the predicted path. And then, on December 27, 2004, just days after Apophis had captured global attention, a researcher made a discovery that would change everything. It was a pre-covery image, a photograph taken back in March 2004, 3 months before Apophis's official discovery, by an automated survey telescope. The asteroid was there in the image, a faint dot among thousands of others, overlooked at the time because no one knew to look for it. But now, with Apophis's approximate orbit known, researchers could go back through archival images and search for earlier sightings. That single overlooked photograph extended the observation arc by 9 months. And in orbital mechanics, 9 months of additional data can transform uncertainty into clarity. The orbit calculation was rerun with the pre-covery image included, and the results were definitive. Apophis would not hit Earth in 2029. The probability dropped from 2.7% to 0. The Torino scale rating plummeted from 4 to 0. The threat was over. But here's the twist that few people realized at the time. While the 2029 impact was ruled out, new concerns immediately emerged about 2036 and 2068. The story wasn't over. It was just beginning. For years, the question hung in the air, subtle and persistent. But observation by observation, radar measurement by radar measurement, the uncertainties shrank. By 2021, after a particularly detailed set of radar observations captured Apophis with exquisite precision, NASA and international partners announced what many had long suspected. Apophis posed no threat to Earth for at least the next 100 years. Not in 2029, not in 2036, not in 2068. The serpent of chaos would pass by harmlessly, and we would be safe. Yet the story of Apophis reminds us of something profound. Our planet orbits the sun in a crowded neighborhood. There are thousands of near-Earth asteroids, many still undiscovered, and some will inevitably pass close. Apophis, once a source of fear, has become a teacher. It has taught us how to track asteroids with precision, how to communicate risk without causing panic, and how to prepare for the day when an object on a collision course might actually be found. And now, as 2029 approaches, Apophis is about to teach us something even more valuable. What happens to a large asteroid when it skims past a planet's gravitational embrace? Understanding asteroids, the ancient remnants of our solar system. To understand Apophis, we must first understand asteroids themselves. These objects, often dismissed as mere space rocks, are in fact time capsules from the earliest days of the solar system. They are fragments that never became planets, relics of a violent, chaotic era when the sun was young and worlds were still forming. About 4.6 billion years ago, our solar system was born from a vast cloud of gas and dust, a nebula spinning slowly in the darkness. Gravity pulled material together, and at the center, the sun ignited. Around it, the leftover material began to coalesce. Dust grains stuck together, forming pebbles. Pebbles collided and merged into boulders. Boulders grew into planetesimals, and planetesimals, over millions of years, became the planets we know today. But not everything made it into a planet. Between the orbits of Mars and Jupiter, where conditions were perfect for rocky bodies to form, something went wrong. Jupiter, the giant of our solar system, began its gravitational reign too early. Its immense mass stirred the region, scattering planetesimals before they could merge into a single world. The story of what happened in this region is written in computer simulations and mathematical models that reconstruct the early solar system's evolution. As Jupiter grew, reaching perhaps 10 or 20 times Earth's mass within the first million years, its gravity began to dominate the region between Mars and the outer planets. Planetesimals that might have coalesced into a single world were instead accelerated to higher velocities. When they collided, instead of gently merging, they shattered. Fragments scattered across the region, and those fragments became the seeds of the asteroid belt. Over time, continued collisions ground larger objects into smaller ones, creating the size distribution we see today, with a few large asteroids like Ceres and Vesta, and millions of smaller fragments. This process, called collisional grinding, continues even now. Every few million years, somewhere in the asteroid belt, two objects collide at high speed, creating a spray of fragments that spread outward. Some of these fragments are captured into families, groups of asteroids with similar orbits and compositions that clearly originated from the same parent body. By studying these families, astronomers can reconstruct the history of collisions in the belt and learn about the internal structure of the objects that were destroyed. Instead of a planet, we got the asteroid belt, a broad ring of debris that orbits the sun like a graveyard of cosmic ambitions. But calling it a graveyard is perhaps misleading. The asteroid belt is not dead, but dynamic. Objects within it continue to collide, evolve, and occasionally escape, venturing inward toward the sun and the rocky planets. The belt is a reservoir of building blocks, a museum of planetary formation, and a source of both danger and opportunity for Earth. Most asteroids reside in this belt, roughly 329 million kilometers from the sun. They are diverse in size, shape, and composition. The largest, Ceres, is nearly 1,000 kilometers across and classified as a dwarf planet. The smallest are mere pebbles, fragments chipped off larger bodies in ancient collisions. Altogether, the asteroid belt contains millions of objects, but their combined mass is less than that of Earth's moon. If you could gather every asteroid in the belt and compress them into a single sphere, it would be smaller than our lunar companion. Asteroids are often categorized by their composition, which reveals where and how they formed. The most common type, making up about 75% of known asteroids, are the C-type, or carbonaceous asteroids. These are dark, almost black, because they're rich in carbon. They formed in the cooler, outer regions of the asteroid belt, where temperatures allowed volatile compounds and organic materials to condense. C-type asteroids are among the most primitive objects in the solar system, virtually unchanged since their formation. Studying them is like peering into the distant past, examining the raw ingredients from which planets were built. The second most common type, accounting for about 17% of asteroids, are the S-type or silicaceous asteroids. These are made primarily of silicate minerals and metallic iron and nickel, giving them a rockier, more stony appearance. They're brighter than C-types, reflecting about 20% of the sunlight that strikes them. S-types dominate the inner asteroid belt, where temperatures were higher during the solar system's formation. They're thought to be similar in composition to certain meteorites that fall to Earth, the ordinary chondrites, which are among the most common types of space rocks found on our planet's surface. Apophis is an S-type asteroid. Its spectrum shows the characteristic signatures of silicate minerals, with absorption features around 1 and 2 micrometers that indicate the presence of olivine and pyroxene, the same minerals found in Earth's mantle. This makes Apophis representative of a large population of near-Earth objects, and studying it will help scientists understand the physical properties of asteroids that might one day threaten our planet. The third major category, the M-type or metallic asteroids, are composed primarily of nickel and iron. These are thought to be the exposed cores of ancient planetesimals that were shattered in collisions early in the solar system's history. When these bodies formed, they were large enough and hot enough to partially melt, causing heavier metals to sink to the center. Later impacts stripped away the outer rocky layers, leaving behind dense metallic cores. The largest known M-type asteroid is Psyche, and NASA's Psyche mission, launched in 2023, is currently on its way to study this fascinating object. Not all asteroids remain in the belt. Gravitational interactions with Jupiter and Mars, along with collisions between asteroids, can nudge objects onto new orbits. Some are flung outward, becoming distant wanderers in the outer solar system. Others are pushed inward, crossing the orbits of the inner planets. These are the near-Earth objects, or NEOs, and they represent both a threat and an opportunity. Near-Earth objects are defined as asteroids or comets whose orbits bring them within 1.3 astronomical units of the Sun. 1 astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. NEOs are further classified into subgroups based on their orbital characteristics. Atens have orbits smaller than Earth's, spending most of their time inside our planet's path around the Sun. Apollos cross Earth's orbit, swinging inward and outward. Amors approach Earth from the outside, but don't quite cross our orbit. And then there are the Ateras, rare objects whose orbits lie entirely within Earth's, making them difficult to detect because they're always in the direction of the Sun. Among these NEOs, some are designated as potentially hazardous asteroids, or PHAs. To earn this classification, an asteroid must be larger than 140 meters in diameter and pass within 0.05 AU of Earth's orbit, roughly 7.5 million kilometers. This might sound like a comfortable distance, but in cosmic terms, it's uncomfortably close. Orbital mechanics are complex, and gravitational interactions can alter paths over time. An asteroid that passes harmlessly today might, after a few close encounters with planets, find itself on a collision course years or centuries hence. As of early 2025, astronomers have cataloged more than 36,000 near-Earth objects, and the list grows longer every year. Surveys like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera Rubin Observatory continuously scan the skies, searching for faint moving dots that betray the presence of asteroids. Each discovery adds to our understanding of the population, helping scientists assess the overall risk and identify objects that warrant closer scrutiny. But finding asteroids is only the beginning. Once discovered, they must be tracked, their orbits calculated with precision. And this is where the story of Apophis becomes particularly fascinating, because tracking an asteroid over decades reveals subtle effects that most people never consider. Forces so small they seem negligible, yet powerful enough to change an orbit by thousands of kilometers. The science of tracking, precision, patience, and the Yarkovsky effect. When astronomers discover a new asteroid, they begin with only a few observations, snapshots of the object's position in the sky taken hours or days apart. From these initial measurements, they calculate a preliminary orbit, a rough estimate of where the asteroid is going and how close it might come to Earth. But orbits are never perfect from the start. There are always uncertainties, regions of possibility rather than certainty. As more observations accumulate, those uncertainties shrink, and the predicted path becomes clearer. For Apophis, this process unfolded over years. After its discovery in 2004, astronomers around the world contributed observations. Optical telescopes tracked its position against the stars. Radar observatories bounced radio waves off its surface, measuring its distance and velocity with extraordinary precision. Each new data point refined the orbit, narrowing the range of possible futures. Radar, in particular, is a powerful tool for asteroid tracking. When a powerful radio signal is transmitted toward an asteroid, a tiny fraction of that signal reflects back to Earth. By analyzing the echo, astronomers can measure the asteroid's distance to within a few meters and its velocity to within millimeters per second. Radar observations also reveal details about the asteroid's size, shape, and rotation. For Apophis, radar images from the Goldstone Deep Space Communications Complex in California and the Green Bank Observatory in West Virginia showed that the asteroid is elongated, somewhat like a peanut, with a length of about 450 meters along its longest axis. But even with the best observations, predicting an asteroid's orbit decades into the future is not straightforward. The problem is that asteroids are not simply governed by the gravitational pull of the sun. They also feel the tug of planets as they pass nearby. They experience the pressure of sunlight, a tiny force that can, over time, nudge them off course. And they're affected by a subtle, often overlooked phenomenon called the Yarkovsky effect. The Yarkovsky effect is named after a Polish-Russian civil engineer, Ivan Osipovich Yarkovsky, who first described it around the year 1900. It's a thermal radiation force, a consequence of the fact that asteroids are not perfect reflectors of sunlight. When the sun shines on an asteroid's surface, the material heats up. But it doesn't cool down immediately when the surface rotates into shadow. There's a delay, a thermal lag, because rocks have thermal inertia. They hold onto heat for a while before radiating it away as infrared light. This delayed re-radiation creates a tiny thrust, like a rocket engine firing in the wrong direction, or perhaps the right one, depending on the asteroid's rotation. If an asteroid spins in the same direction as it orbits, known as prograde rotation, the warmest part of its surface is on the afternoon side, trailing behind in the orbital direction. When that hot surface radiates heat, the emitted photons carry momentum, and by Newton's third law, the asteroid experiences a recoil force, pushing it forward along its orbit. This causes the asteroid to gradually spiral outward, away from the sun. Conversely, if the asteroid spins in the opposite direction, known as retrograde rotation, the warmest surface is on the morning side, ahead in the orbital direction. The recoil pushes the asteroid backward, causing it to spiral inward toward the sun. The effect is incredibly small, equivalent to the weight of a few grapes pushing on a 500-meter wide rock. But space is patient, and over years, decades, or centuries, the Yarkovsky effect can shift an asteroid's orbit by thousands of kilometers. For Apophis, measuring the Yarkovsky effect was crucial. In 2020, astronomers David Tholin and David Farnokia analyzed observations of Apophis and detected the effect directly for the first time. They found that the asteroid's semi-major axis, the average distance from the Sun, was decreasing by about 170 meters per year. This might sound tiny, but over time, it accumulates. By 2029, the Yarkovsky effect will have shifted Apophis's position along its orbit by a measurable amount, altering the exact time and distance of its close approach to Earth. Then came an even more remarkable achievement. In March 2021, using radar observations from the Goldstone Deep Space Communications Complex and optical data from multiple telescopes, Apophis became the asteroid with the most precisely measured Yarkovsky effect ever recorded, surpassing even Bennu, which had been studied up close by NASA's OSIRIS-REx spacecraft. The signal-to-noise ratio of the detection reached 186.4, meaning the measurement was extraordinarily reliable. This precision wasn't just a technical triumph, it was the key that finally unlocked Apophis's future. Understanding the Yarkovsky effect was also essential for ruling out future impacts. Early in Apophis's observational history, there was concern about a so-called gravitational keyhole. This is a small region of space, only a few hundred meters wide, through which Apophis might pass during its 2029 flyby. If the asteroid passed through the keyhole, Earth's gravity would deflect it onto a path that could lead to a collision in 2036. The keyhole concept is a reminder of how sensitive orbital dynamics can be. A tiny difference in position during one flyby can cascade into a dramatically different outcome years later. But as observations improved, it became clear that Apophis would not pass through the keyhole. The asteroid's trajectory was refined to such precision that the uncertainty region, the cloud of possible positions, shrank to a size smaller than the keyhole itself. And in 2021, following radar observations that captured Apophis with the highest fidelity ever achieved for an asteroid, astronomers announced with confidence that the 2036 impact scenario was off the table. So was the 2068 encounter, another date that had once raised eyebrows. Apophis was no longer on any risk list. This refinement process is a testament to the power of patient, methodical science. It took nearly 2 decades of observations, countless hours at telescopes, and sophisticated mathematical models to transform Apophis from a potential threat into a known, safe visitor. And along the way, astronomers developed new techniques and tools that will serve humanity well in the future, should a genuinely dangerous asteroid ever be discovered. But the story of Apophis doesn't end with the elimination of impact risk. In fact, in many ways, the most exciting chapter is just beginning. Because in April 2029, Apophis will pass so close to Earth that it will become the most intensively studied asteroid in history, a natural laboratory for planetary science, and a test case for planetary defense. April 13th, 2029. A Friday to remember. Mark your calendar. April 13th, 2029. A Friday because the universe, it seems, has a sense of irony. On that day, Apophis will make its closest approach to Earth, sweeping past at a distance of about 32,000 kilometers from our planet's surface. To put that in perspective, that's closer than the ring of geostationary satellites that orbit at an altitude of roughly 36,000 kilometers. Communication satellites, weather satellites, and other spacecraft will be positioned farther from Earth than Apophis at its nearest point. The asteroid will skim past, threading the gap between Earth and our artificial moons. The close approach will occur at approximately 6:45 p.m. Eastern Daylight Time, though the exact timing depends on final orbital refinements as the date approaches. For observers on the ground, the spectacle will unfold over the course of several hours. Apophis will first become visible as it rises above the horizon in the eastern sky, appearing initially as a faint point of light. But as it draws closer, it will brighten, reaching an apparent magnitude of about 3.1 at its peak. This is comparable to the brightness of stars in the Big Dipper, easily visible to the naked eye under reasonably dark skies. The visibility zone will favor the Eastern Hemisphere. People across Europe, Africa, and Western Asia will have the best seats in the house. From locations like Paris, Cairo, Istanbul, or Nairobi, observers will be able to watch Apophis drift across the sky like a slow-moving star. It won't streak by like a meteor. Instead, it will glide steadily, covering roughly the width of the full moon every few minutes. Over the course of an evening, its position will shift noticeably, a living demonstration of orbital mechanics playing out in real time. For those equipped with binoculars or small telescopes, the view will be even more rewarding. Apophis's elongated shape might become apparent, a faint, oval smudge rather than a perfect point. And as it moves through the sky, it will pass in front of background stars, a phenomenon that astronomers call an occultation. Precise timing of these occultations can reveal subtle details about the asteroid's shape and size. Amateur astronomers with accurate timing equipment will contribute to the scientific effort, joining professional observatories in a coordinated global campaign to squeeze every bit of information from the encounter. The path of maximum brightness will trace across the Eastern Hemisphere, favoring observers in a band that stretches from Western Europe through the Middle East, across parts of Asia, and down into Africa. In cities like London, Istanbul, Dubai, Mumbai, and Nairobi, the asteroid will pass nearly overhead, reaching its peak brightness and moving most rapidly across the sky. For these locations, Apophis will be unmissable, a celestial event that dominates astronomical conversation and draws crowds to parks, observatories, and rooftops. But even in less favored locations, the event will not go unnoticed. In the Americas, observers may catch the asteroid rising or setting, seeing it low on the horizon, where atmospheric extinction dims its light, but adds a dramatic quality to the observation. In the Western Pacific and Australia, the timing will be less favorable, with Apophis positioned in daylight or twilight for much of the close approach. But as the hours pass and Earth rotates, more and more observers will join the vigil, tracking the asteroid as it recedes back into deep space. The media coverage will be extensive. News organizations around the world will prepare special reports, streaming live feeds from observatories, and interviewing astronomers about the significance of the event. Social media will explode with images, videos, and real-time updates as millions of people share their observations. It will be, quite possibly, the most documented astronomical event in history, a moment when professional science and public enthusiasm converge on a single, moving point of light in the night sky. An estimated 2 billion people will be in regions where Apophis is visible, weather permitting. To put that in perspective, that's more than 4 times the number who watched Neil Armstrong walk on the moon in 1969, about 530 million people. It will be one of the most widely witnessed astronomical events in human history, a cosmic show that requires no special equipment, no tickets, no screens. Just a clear sky and a sense of wonder. And unlike a meteor, shower, or eclipse, this event will unfold slowly enough that you can call your friends, walk outside, and still catch most of it. But the close approach is more than a spectacle. It's a rare opportunity for science that borders on the unprecedented. Close encounters between Earth and asteroids the size of Apophis occur, on average, only once every 7,500 years. The last time an object this large came this close, humans were just beginning to develop agriculture. Cave paintings were still being created in some parts of the world. This is the first time in all of recorded history that an asteroid of this size has approached so closely while being tracked in advance. We have years to prepare, to coordinate observations, to design experiments. The data gathered during the flyby will transform our understanding of asteroids in ways we can barely predict. One of the most significant effects of the close approach will likely be gravitational. As Apophis sweeps past, Earth's gravity will exert tidal forces on the asteroid, squeezing and stretching it in subtle ways. Scientists predict these tidal forces might trigger tiny asteroid quakes, seismic vibrations propagating through the asteroid's interior. The magnitude of these effects will depend on Apophis's internal structure. If the asteroid is a loosely bound rubble pile, a collection of rocks held together by gravity rather than cohesive strength, these vibrations could cause surface material to shift, boulders to tumble, and dust to lift from the surface. If the asteroid is more solid, a coherent chunk of rock, the effects should be different, perhaps less dramatic, but still measurable. The 2029 flyby will provide the first opportunity to test these predictions directly. The tidal forces may also affect Apophis's rotation. The asteroid currently spins once every 30 hours or so, but as it passes Earth, the gravitational interaction could impart a torque, speeding up or slowing down the rotation, depending on the precise geometry of the encounter. Based on computer simulations, measuring this change will provide valuable information about the asteroid's internal structure, its mass distribution, and its mechanical properties. These aren't just academic questions. Understanding how asteroids respond to gravitational stress is crucial for planetary defense. If we ever need to deflect a dangerous asteroid, knowing whether it's solid or rubble pile will determine which deflection strategy works best. Earth's gravity will also alter Apophis's orbit around the Sun. Before the encounter, Apophis is classified as an 18 asteroid, with an orbital period slightly less than Earth's, about 323 days. After the encounter, its orbit will be stretched, elongated by the gravitational deflection. It will become an Apollo asteroid, with an orbital period exceeding Earth's, roughly 378 days. The asteroid will move outward, its path around the Sun widened by the encounter. This transformation from 18 to Apollo is a natural experiment in orbital dynamics, a chance to observe gravitational physics in action on a planetary scale. And then there are the spacecraft. In the years leading up to 2029, 2 missions will rendezvous with Apophis, accompanying it through the close approach and studying it in exquisite detail. The story of how we got these missions is itself remarkable. NASA's OSIRIS-REx spacecraft successfully returned samples from asteroid Bennu to Earth in September 2023, completing its primary mission in spectacular fashion. But the spacecraft was still healthy, with fuel remaining and all instruments functioning. Rather than let it drift into retirement, NASA made a bold decision: redirect it to Apophis. The spacecraft was renamed OSIRIS-APEX, OSIRIS-Apophis Explorer, and sent on a new trajectory that will bring it to the asteroid in June 2029, just weeks after the close encounter with Earth. OSIRIS-APEX will begin imaging Apophis as it approaches Earth in early 2029, capturing the encounter from a unique vantage point in space. After the flyby, the spacecraft will spend 18 months in orbit around Apophis, mapping its surface, analyzing its composition, and performing experiments designed to reveal what lies beneath the surface. The mission represents an extraordinary value, a $1 billion asteroid mission achieved by repurposing an existing spacecraft. One particularly intriguing experiment involves using the spacecraft's thrusters to stir up dust and rocks on Apophis's surface. By firing downward while hovering close to the asteroid, OSIRIS-APEX could create a plume of debris, exposing material that has been buried for billions of years. This technique, which the spacecraft successfully demonstrated at Bennu, allows scientists to peer beneath the weathered surface layer and study pristine material that has been shielded from the harsh environment of space. The European Space Agency's Ramses mission, if approved at the crucial Ministerial Council meeting in November 2025, will take a different and potentially even more dramatic approach. The mission is planned to launch in April 2028 and arrive at Apophis in February 2029, 2 months before the close encounter. Ramses would observe the asteroid before, during, and after its passage past Earth, providing a comprehensive before and after comparison. By tracking changes in the asteroid's shape, spin, and surface features, Ramses could directly measure the effects of Earth's gravitational influence in real time. The mission might even attempt something never before achieved, deploying a small CubeSat to touch down on Apophis' surface and detect seismic waves traveling through the rock. If successful, it would be only the third planetary body, after the Moon and Mars, where we've measured internal seismic activity. Imagine being able to hear an asteroid's interior as Earth's gravity squeezes it. The vibrations, the shifts, the subtle movements that reveal whether it's solid rock or a loose pile of rubble barely holding together. This data would be invaluable, not just for understanding Apophis, but for preparing to deflect any future asteroid threat. Together, these missions will gather data that no Earth-based telescope could obtain. They'll see details invisible from the ground, measure forces too subtle to detect from a distance, and answer questions that have puzzled scientists for decades. How strong is the surface? How porous is the interior? How does an asteroid respond when squeezed by a planet's gravity? The answers will have implications far beyond Apophis. They'll inform planetary defense strategies, helping scientists understand how best to deflect an asteroid if one is ever found on a collision course. They'll shed light on the origins of the solar system, revealing how asteroids formed and evolved. And they'll inspire a new generation of scientists and engineers, reminding us all that space is not distant and untouchable, but close, dynamic, and full of surprises. The keyhole and the future. Beyond 2029. For all the excitement surrounding the 2029 flyby, there was a time when astronomers worried about what might come after. The concern centered on a phenomenon called a gravitational keyhole, a concept that sounds more like science fiction than reality, but is grounded in straightforward orbital mechanics. Imagine Apophis approaching Earth in 2029. Its trajectory is well understood, and we know it will miss us. But space is vast, and even a small uncertainty in the asteroid's exact position translates into a range of possible paths. If Apophis passes through one particular region of space, a tiny zone only a few hundred meters wide, Earth's gravity will bend its orbit in just the right way to set up a collision 7 years later, in 2036. This tiny region is the keyhole. It's not a physical object, but rather a mathematical construct, a volume of space where the conditions for a future impact a line. Think of it like threading a needle. If Apophis passes to one side of the keyhole, it's deflected onto a safe trajectory. If it passes to the other side, it's also safe. But if it passes directly through, the deflection sends it onto a path that intersects Earth's orbit in 2036. The keyhole concept was first proposed by researchers studying Apophis's early orbit. In the mid-2000s, when uncertainties about the asteroid's position were still large, the keyhole represented a genuine concern. If the asteroid passed through it, the probability of a 2036 impact would jump from negligible to significant. But as observations continued, the uncertainty region shrank. By 2013, radar observations had refined Apophis's position so precisely that the keyhole scenario could be ruled out with confidence. The asteroid would pass well outside the keyhole, and the 2036 impact was off the table. But eliminating 2036 didn't end the discussion. What about subsequent encounters? Apophis will continue to cross Earth's orbit for himself, centuries to come. And while most of these encounters will be distant, some might be close. Could a future flyby, decades or centuries from now, set up a collision even farther in the future? The short answer is no. By 2021, after the most detailed radar observations of Apophis ever conducted, astronomers were able to rule out any impact for at least the next 100 years. The asteroid's orbit is now known with such precision that uncertainties about its position a century hence are still smaller than the size of Earth itself. Apophis will pass close several times over the coming decades, in 2036, 2051, and 2116, but none of these encounters will result in an impact. However, there is a subtle caveat that emerged in 2024, and it's worth mentioning because it illustrates just how thoroughly scientists examine every possibility. A study by astronomer Paul Wiegert and colleagues raised an intriguing, if extremely remote, scenario. While Apophis itself poses no threat, the researchers calculated that there is an extraordinarily tiny chance, less than 1 in a billion, that an unknown asteroid could collide with Apophis before the 2029 flyby, potentially nudging it off course. The odds of such a collision happening are already vanishingly small. The odds that such an impact would deflect Apophis toward Earth rather than away from it are even smaller. And even if both unlikely events occurred, the deflection would need to be precisely the right magnitude and direction to create a threat. String these probabilities together, and you get a scenario so unlikely it barely registers as a possibility. It's far more likely you'll be struck by lightning while holding a winning lottery ticket. But the study serves an important purpose. It reminds us that space is full of surprises, and that even well-understood scenarios can hide subtle complexities. It also demonstrates the thoroughness of modern planetary defense. Scientists don't just calculate the obvious risks. They explore even the most remote possibilities to ensure nothing is overlooked. Looking farther into the future, Apophis's orbit will continue to evolve, shaped by gravitational interactions with Earth and other planets, as well as the slow, persistent nudge of the Yarkovsky effect. Over millennia, its path will drift, and encounters that seem distant now might become closer, or vice versa. Predicting an asteroid's orbit centuries or millennia into the future is a challenge, not because the physics is uncertain, but because tiny uncertainties in the present amplify over time. A millimeter per second error in velocity today can become a 1,000-kilometer error 1,000 years hence. But this is where the 2029 flyby becomes invaluable. By observing Apophis up close, measuring its mass, shape, spin, and surface properties with unprecedented precision, scientists will improve their models dramatically. The data gathered in 2029 will anchor future predictions, reducing uncertainties and allowing astronomers to forecast Apophis's path with confidence for centuries to come. And in a broader sense, Apophis serves as a prototype for how humanity should approach the asteroid threat. It's a test case, a trial run for the systems and strategies we'll need if a genuinely dangerous asteroid is ever discovered. Every observation of Apophis, every refinement of its orbit, every mission planned to study it, contributes to a growing body of knowledge and experience. We're learning how to track asteroids, how to communicate risk, how to mobilize international cooperation, and how to design missions that can intercept and study these objects. Apophis has already taught us that the initial assessment of an asteroid's threat can be overly pessimistic. Early observations often suggest higher risks than turn out to be real. It has taught us the importance of patience and precision. And it has taught us that the universe is not out to get us, but that vigilance is warranted. Space is vast, but it is not empty, and the occasional close encounter is inevitable. Chavad. Planetary defense, from observation to action. The story of Apophis is inseparable from the broader story of planetary defense, humanity's effort to identify, track, and, if necessary, deflect asteroids that threaten Earth. For most of history, asteroid impacts were acts of fate, unpredictable and unstoppable. Today, for the first time, we have the technology to see them coming and, potentially, to do something about it. Planetary defense begins with detection. You can't deflect an asteroid if you don't know it's there. Over the past few decades, surveys like the Catalina Sky Survey in Arizona, the Pan-STARRS telescopes in Hawaii, and the Atlas system have scanned the skies night after night, building a catalog of near-Earth objects. The goal is to find as many potentially hazardous asteroids as possible, ideally decades before any potential impact, giving humanity time to respond. As of early 2025, astronomers have cataloged more than 36,000 near-Earth objects, and it's estimated that about 90% of asteroids larger than 1 kilometer have been found. These are the objects capable of causing global catastrophes, mass extinctions, and climate-altering impacts. But smaller asteroids, those in the 140 meter to 1 kilometer range, are more numerous and harder to find. Current estimates suggest that only about 40% of these have been discovered, leaving thousands still lurking in the shadows. The upcoming Vera Rubin Observatory, scheduled to begin operations in 2025, will dramatically accelerate the search. With its wide field of view and sensitive detectors, Rubin will survey the entire visible sky every few nights, detecting faint, fast-moving objects that other telescopes miss. It's expected to double the number of known near-Earth asteroids within its first year of operation, and within a decade, it could catalog the vast majority of potentially hazardous objects. But finding asteroids is only the first step. Once discovered, they must be tracked, their orbits refined, and their threat assessed. This is where tools like the Torino scale and Palermo scale come into play. The Torino scale, as mentioned earlier, is a simple, color-coded system designed to communicate risk to the public. It ranges from 0, indicating no hazard, to 10, a certain collision capable of global devastation. The scale takes into account both the probability of impact and the estimated size of the asteroid, combining them into a single number. The Palermo scale, on the other hand, is a more technical tool used by specialists. It compares the likelihood of a detected impact with the background hazard, the average risk posed by all asteroids over time. A Palermo scale value of 0 means the detected threat is equal to the background risk. Positive values indicate a threat greater than average, warranting attention. Negative values, which are more common, indicate a threat less than the background and generally not cause for concern. Most asteroids, when first discovered, have Palermo scale values well below 0, and as observations refine their orbits, the values drop even further. Apophis holds the distinction of having reached the highest Palermo scale value ever recorded, 1.10, during the brief period in late 2004 when a 2029 impact seemed possible. This meant the threat was more than 12 times greater than the background hazard, a level that prompted immediate action. But as observations continued, the value plummeted, eventually dropping below 0 and disappearing from risk tables entirely. If an asteroid is found to pose a genuine threat, the next question is, what do we do about it? This is where planetary defense transitions from observation to action. Several deflection strategies have been proposed, each with its own advantages and challenges. The most straightforward method is the kinetic impactor, which involves crashing a spacecraft into the asteroid at high speed. The impact transfers momentum to the asteroid, nudging it off course. The key is to do this years or decades in advance, when even a small change in velocity can translate into a large change in position by the time the asteroid reaches Earth. The earlier the deflection, the smaller the nudge required. In September 2022, NASA's Double Asteroid Redirection Test, or DART, successfully demonstrated this technique in what became humanity's first successful planetary defense mission. DART was a refrigerator-sized spacecraft that deliberately crashed into Dimorphos, a small moon orbiting the larger asteroid Didymos. The impact occurred at a speed of about 22,500 kilometers per hour. The result exceeded even the most optimistic predictions. Before impact, scientists had defined success as changing Dimorphos' orbit by at least 73 seconds, barely more than a minute. When the dust settled and observations were complete, the actual change was stunning. 32 minutes. The mission had exceeded its minimum benchmark by more than 25 times. The impact excavated a large amount of material. And here's where it gets interesting. The recoil from the ejected debris enhanced the momentum transfer dramatically. The measured momentum enhancement factor, called beta, was 3.6, meaning the impact transferred roughly 3.6 times more momentum than if the asteroid had simply absorbed the spacecraft without ejecting any material. This discovery transformed our understanding of kinetic impacts. It means we could use either a smaller spacecraft or have shorter lead times to produce a given deflection than previously expected. The ejected material acts like a rocket engine firing in reverse, amplifying the push. For planetary defense, this is excellent news. Deflecting an asteroid is more effective than we thought. But kinetic impactors are not the only option. Another strategy is the gravity tractor, a concept that sounds almost gentle by comparison. A gravity tractor is a spacecraft that hovers near an asteroid for an extended period, months or years. Though the spacecraft's gravity is tiny, over time, it exerts a slow, steady pull on the asteroid, gradually altering its orbit. This method requires patience and precise navigation, but it has the advantage of being non-invasive. There's no risk of fragmenting the asteroid or causing unintended consequences. The spacecraft simply parks itself near the asteroid and lets mutual gravitational attraction do the work. The physics of a gravity tractor are elegant in their simplicity. Every object with mass exerts a gravitational pull on every other object. Though a spacecraft might weigh only a few hundred kilograms, and an asteroid might weigh millions of tons, the gravitational force between them, while tiny, is real. If the spacecraft positions itself carefully, hovering at a fixed distance from the asteroid and using its thrusters to maintain position, the gravitational attraction will slowly pull the asteroid toward the spacecraft. As the spacecraft moves, the asteroid follows, its orbit gradually bending. The key advantage of a gravity tractor is control. Unlike a kinetic impact, which delivers a single, powerful impulse, a gravity tractor provides continuous, adjustable force. If the asteroid isn't responding as predicted, the spacecraft can change position or thrust differently. And because there's no impact, there's no risk of creating debris or altering the asteroid's spin in unpredictable ways. The downside is time. A gravity tractor requires years of operation to produce a significant deflection, making it suitable only for threats detected well in advance. For larger asteroids, or for situations where time is short, more dramatic measures might be necessary. Nuclear deflection, often misunderstood and sensationalized, is a serious option. The idea is not to blow up the asteroid, which would only create more problems, but to detonate a nuclear device near its surface. Explosion would vaporize a layer of material on one side, and the expanding vapor would act like a rocket engine, pushing the asteroid in the opposite direction. Studies suggest that nuclear deflection could be highly effective, even against large asteroids, but it requires careful planning and international cooperation. The challenge with nuclear deflection is not the physics, which is well understood, but the politics. Under the Outer Space Treaty of 1967, nuclear weapons are prohibited in space. Any use of nuclear technology for asteroid deflection would require international agreement and oversight. It would need to be clearly defensive, with no possibility of the technology being weaponized or misused. Discussions about this are ongoing in forums like the United Nations Committee on the Peaceful Uses of Outer Space, where representatives from spacefaring nations debate how to balance planetary defense needs with non-proliferation concerns. International cooperation is, in fact, a cornerstone of planetary defense. Asteroids do not respect borders, and an impact anywhere on Earth would have global consequences. Organizations like the International Asteroid Warning Network and the Space Mission Planning Advisory Group coordinate efforts among space agencies, sharing data, planning missions, and developing response strategies. If a dangerous asteroid is ever found, the response will need to be coordinated, transparent, and swift. Apophis, though it poses no threat, has become a valuable test case for these systems. The missions plan to study it, Osiris, Apex, and Ramses, are exercises in international collaboration. The data they gather will inform planetary defense models, helping scientists understand how asteroids respond to gravitational perturbations and how best to deflect them if necessary. And perhaps most importantly, Apophis has reminded the world that asteroid threats are real, but manageable. They're not the stuff of disaster movies, but of careful science, patient observation, and thoughtful preparation. The serpent of chaos, once feared, has become a teacher. And in 2029, it will pass by safely, a symbol of humanity's growing ability to understand and, when necessary, protect itself from the cosmos. The Physics of Apophis, Portrait of a Cosmic Wanderer. To truly understand Apophis, we must look beyond its trajectory and delve into its physical nature. What is this object really? What is it made of? How does it move through space? And what can its properties tell us about the broader population of near-Earth asteroids? Apophis is classified as an S-type asteroid, meaning it's composed primarily of silicate minerals, rocky materials similar to those found in Earth's crust and mantle. Spectroscopic observations, which analyze the sunlight reflected off the asteroid's surface, reveal absorption features characteristic of olivine and pyroxene, magnesium, and iron-rich silicates. These minerals are the building blocks of rocky planets, and their presence in Apophis suggests the asteroid formed in the inner solar system, where temperatures were high enough for silicates to condense from the primordial solar nebula. S-type asteroids are moderately bright compared to darker C-type asteroids. They reflect about 20% of the sunlight that strikes them, giving them an albedo of roughly 0.20. This reflectivity, combined with Apophis's size, makes it relatively easy to observe, even from great distances. But easy is relative. Apophis is still a small object in the vastness of space, and detecting it requires sensitive instruments and careful timing. The asteroid's size is estimated at about 340 meters in diameter, though this is an average. Radar observations have shown that Apophis is not a perfect sphere, but rather an elongated, irregular body. Its longest axis stretches to about 450 meters, while its shortest is closer to 170 meters. This peanut-like shape is not uncommon among asteroids, and it's thought to result from the way these objects formed and evolved through collisions, gravitational interactions, and the slow accumulation of debris. Apophis's mass is more difficult to determine. Without a natural satellite, astronomers can't directly measure the asteroid's gravitational influence on another object. Instead, they rely on models that combine size estimates with assumptions about density. S-type asteroids typically have densities between 2.7 and 3.5 grams per cubic centimeter, somewhat less than solid rock, because asteroids are often porous, riddled with cracks and voids. Based on these assumptions, Apophis's mass is estimated at roughly 60 million metric tons, though this figure will be refined significantly when Osiris Apex and Ramses study the asteroid up close. The asteroid's rotation is another intriguing feature. Apophis spins once every 30.4 hours, a leisurely pace by asteroid standards. Some asteroids spin so rapidly that they're nearly tearing themselves apart, held together only by gravity and internal friction. Others tumble chaotically, their rotation axes wobbling unpredictably. Apophis, by contrast, appears to have a stable, prograde rotation, spinning in the same direction as it orbits the Sun. But this rotation will not remain constant. When Apophis passes Earth in 2029, tidal forces will exert a torque on the asteroid, altering its spin rate. Depending on the precise geometry of the encounter, the rotation could speed up or slow down, and the spin axis might tilt. Measuring these changes will provide valuable clues about the asteroid's internal structure. If Apophis is a solid, coherent chunk of rock, the changes will be subtle. If it's a rubble pile, a loosely bound collection of boulders held together by gravity, the changes will be more dramatic, and the asteroid's shape might even deform slightly. Surface composition and texture are also areas of active interest. Spectroscopy can reveal the presence of certain minerals, but it can't tell us much about the surface's physical properties. Is it smooth or rough? Dusty or rocky? Are there large boulders or fine regolith, the powdery material that covers many airless bodies in the solar system? Images from Osiris Apex and Ramses will answer these questions, providing the first detailed views of Apophis's surface. The texture of an asteroid's surface tells a story about its history. Smooth surfaces might indicate a covering of fine dust that has accumulated over millions of years through micrometeorite impacts, a process that grinds surface rocks into ever finer particles. Rough, boulder-strewn surfaces suggest recent disruption, perhaps from a collision or from tidal forces during a previous close planetary encounter. Some asteroids show evidence of space weathering, a suite of processes including micrometeorite bombardment and exposure to solar wind that gradually darkens and reddens the surface over time. By analyzing Apophis's surface features, scientists can estimate how long the current surface has been exposed and whether the asteroid has experienced recent geological activity. Another fascinating question is whether Apophis harbors any volatile materials. While S-type asteroids are generally considered dry, lacking the water and organic compounds found in C-type asteroids, some S-types have surprised scientists by showing evidence of hydrated minerals. These minerals formed in the presence of water, perhaps during the asteroid's early history, when it was part of a larger, wetter parent body. If Apophis contains hydrated minerals, it would suggest a more complex formation history than simple models predict. Scientists are particularly interested in comparing Apophis to other asteroids that have been studied up close. The asteroid Itokawa, visited by Japan's Hayabusa mission, is an S-type similar in size to Apophis. Itokawa turned out to be a rubble pile, a collection of rocks ranging from pebbles to house-sized boulders with almost no fine dust. The asteroid Bennu, studied by NASA's OSIRIS-REx, is a C-type, darker and more primitive, but also a rubble pile. Its surface is so rough and boulder-strewn that finding a safe landing site for sample collection was a major challenge. The asteroid Ryugu, studied by Japan's Hayabusa 2, presented similar challenges, with its surface resembling a pile of gravel rather than solid rock. If Apophis is similar to these asteroids, it will have significant implications for planetary defense. Rubble pile asteroids are harder to deflect because they're not solid. A kinetic impactor might excavate a crater and eject material, but the energy is also absorbed by the shifting, fracturing interior. Understanding how different types of asteroids respond to impacts is crucial for designing effective deflection strategies. And then there's the question of origins. Where did Apophis come from? Its orbit suggests it originated in the main asteroid belt, possibly in the inner belt where S-types are common. Gravitational interactions, perhaps a close encounter with Mars or a resonance with Jupiter, could have nudged it onto an Earth-crossing orbit. But without more information, this is speculation. The missions to Apophis may provide clues, particularly if they can analyze the asteroid's composition in detail and compare it to known meteorite samples. One fascinating possibility is that Apophis, like many near-Earth asteroids, could be a fragment of a larger parent body that was shattered in a collision long ago. If so, there may be other fragments out there, siblings of Apophis, drifting through the inner solar system on similar orbits. Identifying and tracking these objects could reveal the history of collisions and disruptions that shaped the asteroid belt over billions of years. But for now, Apophis remains an individual, a solitary wanderer that has captured humanity's attention. In 2029, when it passes close, we will see it not as a distant speck of light, but as a real, tangible world. A small, dark, rocky body carrying the story of the solar system's birth within its ancient stones. The hypothetical impact. Understanding the risk. Though we know Apophis will not hit Earth, it's worth considering, carefully and soberly, what would happen if an asteroid of its size did strike our planet. This is not a thought experiment in fear, but an exercise in understanding the stakes of planetary defense and the importance of the work astronomers are doing. Apophis is about 340 meters across and has an estimated mass of 60 million metric tons. If it were to collide with Earth, it would be traveling at a relative velocity of roughly 12.6 kilometers per second. At that speed, the kinetic energy of the impact would be equivalent to about 1,200 megatons of TNT. To put that in perspective, the largest nuclear weapon ever detonated, the Soviet Union's Tsar Bomba, released about 50 megatons. An Apophis impact would be roughly 24 times more powerful. The effects of such an impact would depend heavily on where it struck. If Apophis hit the open ocean, far from land, the immediate devastation would be limited. But the impact would generate massive tsunamis, waves tens of meters high that could inundate coastlines hundreds or even thousands of kilometers away. The energy released would heat the surrounding water, vaporizing vast quantities and injecting steam and aerosols into the atmosphere. The environmental consequences would be severe, though not globally catastrophic. If Apophis struck land, the destruction would be more concentrated but no less devastating. The impact would create a crater several kilometers across, instantly vaporizing everything within the immediate impact zone. The shockwave would flatten structures for tens of kilometers in all directions. Seismic waves would propagate through the Earth's crust, triggering earthquakes. Thermal radiation from the impact would ignite fires over a wide area. And the atmosphere above the impact site would be heated to incandescent temperatures, creating a blast wave that could cause severe burns and damage far beyond the crater. But this would not be a global extinction event. Apophis is too small for that. Objects in the 300 to 500 meter size range are sometimes called regional impactors. They can devastate an area the size of a small country, but they lack the energy to inject enough debris into the upper atmosphere to trigger a global climate shift. The famous Chicxulub impactor, which contributed to the extinction of the non-avian dinosaurs 66 million years ago, was estimated to be about 10 kilometers across, releasing 100 million megatons of energy, nearly 100,000 times more powerful than an Apophis-sized impact. To put the scale in perspective, consider the 1908 Tunguska event in Siberia. An object estimated to be only 50 to 60 meters across exploded in the atmosphere, flattening 2,000 square kilometers of forest, but causing no direct human casualties because the region was sparsely populated. The Tunguska object released roughly 5 to 15 megatons of energy, far less than Apophis would produce. Yet even that relatively small event left a lasting mark, creating a blast pattern visible from space and generating shockwaves that were recorded around the world. An Apophis impact would be nearly 100 times more powerful than Tunguska, creating devastation on a scale not seen in recorded human history. Still, a regional impact would be a catastrophe. If it struck near a populated area, the death toll could number in the hundreds of thousands or even millions. The economic damage would be staggering, measured in trillions of dollars. Infrastructure across an entire region would be destroyed, and the psychological impact, the knowledge that a rock from space had caused such devastation, would reverberate through human culture for generations. The social and political consequences might persist for decades, affecting everything from urban planning to international space policy. But here's the key point: we would see it coming. If an asteroid the size of Apophis were on a collision course with Earth, astronomers would detect it years, possibly decades, in advance. This is not the scenario of disaster movies, where an asteroid appears suddenly and there's no time to react. Real planetary defense operates on longer timescales, with careful tracking, deliberate planning, and coordinated action. With sufficient warning, a kinetic impactor mission like DART could deflect the asteroid, nudging it just enough to miss Earth. The key is to act early. A deflection of just 1 centimeter per second, applied 10 years before an impact, can shift the asteroid's position by tens of thousands of kilometers by the time it reaches Earth. That's more than enough to turn a direct hit into a safe miss. This is why the work of asteroid surveys is so important. The goal is not to find every asteroid tomorrow, but to find them years or decades before they pose a threat. And it's why missions like DART and the upcoming studies of Apophis are invaluable. They teach us how asteroids behave, how they respond to forces, and how we can protect ourselves. In the case of Apophis, we're fortunate. The asteroid will pass by harmlessly, a cosmic visitor that poses no threat. But it serves as a reminder. Space is not empty. The solar system is full of debris, leftovers from its formation, and occasionally, these objects cross paths with Earth. Most of the time, nothing happens. The distances are vast, and space is mostly empty. But on rare occasions, an impact occurs, and when it does, the consequences can be profound. The history of Earth is written in craters. From the Barringer crater in Arizona, formed about 50,000 years ago by an iron meteorite perhaps 50 meters across, to the buried Chicxulub crater in Mexico, evidence of past impacts is scattered across the globe. Each crater is a reminder that asteroid impacts are not hypothetical. They have happened, they will happen again, and the only question is when. But unlike our ancestors, we are not helpless. We have telescopes to see them coming. We have spacecraft to study them, and we have the beginnings of a planetary defense capability, the tools and knowledge to deflect an asteroid if necessary. Apophis has played a crucial role in developing this capability, and in 2029, it will continue to teach us. The cultural impact, fear, fascination, and the future asteroids occupy a unique place in the human imagination. They are both mundane and terrifying, objects of scientific curiosity, and symbols of cosmic catastrophe. For most of history, humans had no concept of asteroids. Meteorites that fell from the sky were curiosities, sometimes worshipped, sometimes studied, but rarely understood. The idea that chunks of rock could orbit the sun and occasionally strike Earth was not seriously considered until the 19th century. The discovery of asteroids began in 1801 when Giuseppe Piazzi found Ceres, the largest object in the asteroid belt. Over the following decades, more were found, and astronomers began to piece together the picture of a vast belt of debris between Mars and Jupiter. But it wasn't until the 20th century, with the rise of impact geology and the study of craters, that the threat posed by asteroids became clear. The Barringer crater in Arizona, also known as Meteor Crater, was long believed to be volcanic in origin. But in the early 1900s, geologist Daniel Barringer proposed that it was formed by a meteorite impact. The idea was controversial at the time, but as evidence accumulated, it became undeniable. The crater is nearly 1.2 kilometers wide and 170 meters deep, excavated by a meteorite estimated to be 50 meters across. The realization that such a small object could cause such devastation was sobering. The discovery of the Chicxulub crater in the 1990s, linked to the mass extinction 66 million years ago, further cemented the connection between asteroid impacts and catastrophe. The evidence, from shocked quartz to a global layer of iridium-rich clay, painted a picture of a world-ending event. The impact didn't just kill the dinosaurs directly. It triggered global wildfires, tsunamis, and a prolonged impact winter that disrupted ecosystems worldwide. The realization that a single asteroid impact could cause a mass extinction was a turning point in how scientists and the public viewed space. But asteroids are not merely agents of destruction. They are also keys to understanding the solar system's history. The materials that make up asteroids are in many cases, nearly unchanged since the solar system's formation. Studying them is like examining fossils, except these fossils are made of rock and ice, and they orbit the sun rather than lie buried in the ground. Sample return missions, like Japan's Hayabusa and Hayabusa 2, and NASA's OSIRIS-REx, have brought pieces of asteroids back to Earth for detailed analysis. These samples contain organic molecules, water-bearing minerals, and isotopic signatures that reveal the conditions of the early solar system. They've shown that asteroids may have delivered water and organic compounds to the young Earth, playing a role in the origin of life. In this sense, asteroids are both destroyers and creators, agents of chaos and agents of change. The cultural impact of asteroid discoveries like Apophis is complex. On one hand, there is fear. The idea of an asteroid strike taps into deep, primal anxieties about sudden, unstoppable disasters. When Apophis was first discovered and the possibility of a 2029 impact was announced, media coverage often leaned toward sensationalism. Headlines warned of killer asteroids and cosmic threats, sometimes exaggerating the risk and downplaying the uncertainties. On the other hand, there is fascination. Asteroids are messengers from the deep past, windows into the processes that shaped the planets. They're also potential resources, rich in metals and minerals that could one day be mined. And they're accessible, at least compared to other objects in the solar system. A mission to an asteroid is easier, in many ways, than a mission to Mars or the outer planets. Apophis, in particular, has become a cultural icon. It appears in documentaries, science fiction stories, and educational materials. Its name, evoking the ancient Egyptian god of chaos, adds a mythological dimension that resonates with audiences. And the fact that it was once considered a potential threat, only to be ruled out through careful science, makes it a story of triumph. A demonstration that human ingenuity can solve problems once thought insurmountable. The upcoming 2029 flyby will likely intensify public interest. For most people, asteroids are abstract concepts, distant objects that exist only in photographs and data. But in 2029, Apophis will be visible to the naked eye, a real, tangible presence in the night sky. Millions of people will look up and see it moving, a wanderer from the depths of space passing close enough to feel almost within reach. This experience will be educational, but it will also be emotional. It will remind us that we live in a dynamic universe, where change is constant, and where the unexpected can happen. There is also an educational dimension. Teachers, planetariums, and science communicators are already preparing materials for the 2029 flyby. It will be an opportunity to explain orbital mechanics, to discuss planetary defense, and to inspire students to pursue careers in science and engineering. Events like this, rare and spectacular, have a way of capturing the public imagination in ways that routine observations cannot. And finally, there is the philosophical dimension. Asteroids force us to confront the fact that Earth is not isolated. We are part of a solar system, and that system is full of objects that occasionally interact with our planet. For billions of years, impacts have shaped Earth's surface, influenced its climate, and driven evolutionary change. In a very real sense, asteroid impacts are part of the story of life on Earth. The 2029 flyby of Apophis will be a moment to reflect on these themes. It will be a chance to celebrate human achievement, to marvel at the beauty and complexity of the cosmos, and to look forward to a future where asteroid threats are not sources of fear, but challenges that humanity is prepared to meet. Closing reflections. A serpent in the sky. As we drift toward the end of this journey, let's return to where we began. To a mountaintop in Arizona, to 3 astronomers scanning the sky, to a faint dot of light that would become Apophis. The story of this asteroid is, in many ways, a microcosm of how science works and how humanity has evolved in its relationship with the cosmos. It begins with discovery, continues through uncertainty, and arrives at understanding. It involves thousands of people, from astronomers tracking the asteroid, to engineers building spacecraft, to journalists working to communicate the risks and opportunities. But beyond the science, there is something profoundly transformative about this story. For virtually all of human history, hundreds of thousands of years, asteroid impacts were acts of fate, unpredictable and unstoppable. Our ancestors could only watch the sky and wonder. When the Tunguska event flattened 2,000 square kilometers of Siberian forest in 1908, it was observed but not understood. The Barringer crater in Arizona stood for millennia before anyone realized a space rock had created it. The Chicxulub impact that reshaped life on Earth 66 million years ago left no witnesses who could comprehend what had happened. But Apophis represents a turning point. For the first time in the history of life on Earth, a species has the ability to see a potential threat from space decades in advance, track it with extraordinary precision, and, if necessary, do something about it. We've gone from passive observers to active participants in our own survival. That's not just a scientific achievement, it's an evolutionary leap. We are the first species on this planet capable of defending it from cosmic threats. For a brief time, Apophis represented genuine uncertainty, a reminder that the universe is vast, indifferent, and occasionally dangerous. That sense of vulnerability, the realization that our world is not immune to cosmic forces, is humbling. But it's also empowering, because unlike our ancestors, we are not helpless. We have the tools to see threats coming, the knowledge to understand them, and the technology to respond. The name Apophis, the serpent of chaos, carries weight. In mythology, chaos is not merely disorder, but a force of transformation. It's the tension between destruction and creation, the breaking of old patterns to make way for new ones. In this sense, Apophis has lived up to its name. It disrupted our complacency, forcing us to confront the reality of asteroid impacts. It challenged our detection systems, our tracking methods, and our communication strategies. And in doing so, it made us better prepared for the future. In 2029, when Apophis sweeps past Earth, it will be a moment of celebration. Scientists will gather data that will inform planetary defense strategies for generations. Engineers will demonstrate the capabilities of spacecraft designed to study and, if necessary, deflect asteroids. And people around the world will look up and see a visitor from the depths of space, a wanderer that once seemed threatening, but now represents opportunity. But Apophis is also a reminder that the work is not finished. There are thousands of asteroids still undiscovered, and some of them may pose real threats. The surveys must continue. The tracking must improve. The technology must advance. And the international cooperation that has characterized planetary defense efforts must be maintained and strengthened. As you rest tonight, let your mind drift through the story we've traveled. From the moment of discovery to the refinement of orbits, from the elimination of impact scenarios to the planning of missions, Apophis has been a teacher. It has taught us humility, showing that the universe is full of objects we don't yet know about. It has taught us patience, demonstrating that precision takes time and care. And it has taught us hope, proving that threats can be understood, managed, and transformed into opportunities. In a few years, on a Friday evening in April, 2 billion people will have the chance to see Apophis with their own eyes. Some will watch from cities, where light pollution dims the stars, but cannot hide a moving object so close and bright. Others will watch from dark countrysides where the Milky Way stretches overhead and Apophis will glide past like a traveler on an ancient road. Children will point, adults will explain, and somewhere, an astronomer will capture an image, one more data point in a catalog that grows richer with each passing year. For now, the Serpent of Chaos drifts through space, unaware of the names we've given it, the fears it once inspired, or the excitement it now generates. It follows the laws of physics, responding to the pull of the sun, the nudge of planets, and the slow, patient push of thermal radiation. It's just a rock, ancient and silent, carrying within it the story of the solar system's birth. But to us, it's more. It's a symbol of our vulnerability and our resilience. It's a reminder that the cosmos is not distant and abstract, but close and dynamic. And it's a promise that when we look up, whether in wonder or in wariness, we are not alone. We are part of a community of explorers, thinkers, and dreamers who refuse to accept the unknown as unknowable. So rest now. Let the story of Apophis settle into your thoughts like dust on a distant asteroid. Let the numbers fade and the orbits blur. What remains is simpler and more profound. We live in a universe where rocks drift through darkness, where planets spin through space, and where life, fragile and improbable, clings to the surface of one small world. And that life, against all odds, has learned to look up, to see the serpent approaching, and to greet it not with fear, but with curiosity. If this journey through the cosmos helped you unwind tonight, or sparked your curiosity about the wonders above, consider subscribing to the Sleepy Science channel. We're here to explore the universe at a pace that lets you rest, to turn grand mysteries into gentle lullabies. Sleep well. Dream of distant orbits and quiet encounters. And when April 13th, 2029 arrives, that Friday the 13th, just a few years from now, remember this moment. If you're awake and the sky is clear, look up. Apophis will be there, visible to your naked eyes, a visitor passing through the gap between Earth and our satellites. 2 billion people will witness it together, a global gathering for something that hasn't happened in recorded history and won't happen again for thousands of years. You'll see it move across the stars, not quickly like a meteor, but slowly enough to watch its progress, to point it out to others, to feel the weight of the moment. A space rock the size of 3 football fields, once feared as a world killer, now transformed into humanity's greatest teacher about planetary defense. A serpent in the sky, closer than it sounds and safer than it seems. And you'll be part of history, one of billions watching the cosmos come close enough to touch. Mark your calendar, April 13th, 2029. You won't want to miss it. Until then, rest. The asteroid is still far away, tracing its patient orbit around the sun. The calculations are precise, the threat is past, and the universe, for all its chaos, follows rules we're learning to read. Good night.